In a second, I'm going to talk about Bayesian methods. But first, I'm going to just ask a question is, can we find the perfect value for a coefficient? In all the work we've done so far, remember a lot of the times when we run our models, we're going to get different coefficients each time we run it. Like Maxent tends to come up with different coefficients because there's some stochasticity in there. If we change our field data up, if we're doing cross-validation, our coefficients are always going to be a little different. So the real answer is we can't really. There's enough randomness in our system, especially in ecology, where there isn't going to be a perfect value for a coefficient. Maybe if you have a few values within a categorical coefficient, maybe. But usually what we're looking for is, again, an estimate of a coefficient and some confidence around that or some uncertainty around it. So Bayesian is basically a very different approach, and the idea is around, instead of trying to find a perfect value for our coefficients, we're updating them. And we update them, and in some cases update them and update them and update them. And that's part of the philosophy around Bayesian. And anyway, so what it allows us to do is update an existing probability when there's more data made available. We'll talk more about that in a second. Allows a lot of flexibility to create different types of data, to create probabilities. This is definitely growing in popularity. And one of the reasons is because we have imperfect data. We don't have perfect data, so we need to sort of have the same kind of thought process around our modeling that the human brain does, that the human brain automatically deals with a lot of uncertainty. If someone throws a ball to you and you catch it, and then they throw it again, it's never going to come to exactly the same spot. Your brain is very good at shifting and catching balls, after you learn to do it, of course, and dealing with that stochasticity. So it's trying to get digital computers, which don't deal with stochasticity well. They're not random machines, they're deterministic. It's a way of trying to get them closer to how we actually think. The basic idea comes from this equation, Bayes' theorem, and these definitions are important. And the idea there is we have PA given B, or the probability of A given B, and Thomas Bayes determined that if you didn't have the probability of A given B, but you had some other information, you could compute it from the probability of B given A times the probability of A divided by the probability of B. So the example that helped me get my head around this, and I hope it'll help you, is the idea of predicting landslides. So let's say we'd like to know the probability of landslide given that it's raining. Like, it's raining outside, we're about to send crews down a road that has had landslides in the past. We don't know the probability of landslide given that it's raining, but we have this feeling that when it rains, we have more landslides. The dirt picks up the rain, makes it heavier. We do tend to have more landslides given it's raining, but what's the probability? What's the risk that we're going to have a landslide? Well, we don't have that number, but we could have the probability of landslide simply by take the number of landslides we've had in the last 10 years, divide it by the number of days in 10 years, and we'd have probability. Probability of rain, again, simple. Weather, look at, okay, for those days that we had rain, what's the number of days we had rain over the last 10 years versus the total number of days? Boom. And then probability of rain given that there's a landslide. Now, this is where we'd have to have some field data. Someone would have had to have recorded on every day that we had a landslide, was it raining or not? But that's data we could collect in the field. So once we had those three probabilities, then we can compute the probability of a landslide given that it's raining using this equation, which is really a fairly simple equation, right? It has the probability of B given A times probability of A divided by B. So it's a multiply and a divide. Simple, elegant, interesting to get your mind wrapped around. But okay, so definitions again. Probability of A given B is called the posterior probability. It's called the posterior because it's on the back end of the equation, right? It's after this equation is computed, so it's post. So it's the posterior probability. The probability of A over here is called the prior probability. So the way I look at this is the probability of A that we have right now, like the probability of landslides. That's the prior, and then the posterior is the probability of A given B, or probability of landslides given that it's raining. And then these are simply probabilities of B, either with or without, with A, given A, or probability of B by itself. Cool. The prior has the most controversy around it, because how do we get the prior? Sometimes that's very difficult to obtain. So there's two types of priors. You'll hear about informative priors, where we have prior based on data, like our landslide estimate, or landslide probability. Number of landslides we've had in 10 years divided by the number of days in a year, we get the probability of landslide on each day. But there's something interesting with Bayes, is that if you run Bayes several times, you can actually use uninformed prior. And there's work out there that shows you can just pick one. And then as you apply data, oh, and I should have mentioned, notice that you could run this several times. As you get more information about landslides, you could run this again and keep updating the probability of a landslide given different information. And so if you do that several times, it's been shown that even having an uninformed prior is okay. And there's a principle of indifference, which basically says if you don't know, well, just assign equal probabilities to all outcomes. And this has been shown to work. Again, it's based on, do you have other data you can apply to refine those probabilities, and then it will approach the probability given an informed prior. Okay, so you'll hear about a couple different methods with Bayes. Hierarchical Bayes, it's what we just talked about with multi-level models. You'll hear quite a bit about hierarchical Bayes, because this is the idea that you can use one Bayes equation to then compute your coefficients at the next level, and you can stack them up. And some folks stack them up in quite a few layers. So again, using Bayesian equations to predict your coefficients in different equations in different levels. Bayesian networks are actually making networks. In other words, it doesn't have to necessarily be hierarchical or levels. It could be more complex than that, something like a neural network. And these become networks of equations and distributions. Now, this is one I just need to mention at this point, because if you look at all the different tools we've got, from linear models to GLMs, GAMs, CART, Bayesian, multi-level, we start putting these into these hierarchical and network-based frameworks. You could start to think about having larger hierarchies and networks of different models. Now, no one's really done this yet that I know of, but I think that's where we're headed, is a fair amount of complexity around models. And we'll have a challenge with overfitting and the models being too complex. But the level of flexibility that we're getting with all these different models is really interesting. And then, of course, we have numerical methods and other tools coming in, like neural networks. They're pretty exciting for solving a lot of these problems. Back to Bayes, there's a bunch of different tools out there. WinBugs, it's the original Bayesian modeling package, has the worst user interface I've ever seen in any package. It's horrendous. There's GeoBugs, Laplace's daemon, R packages for Bayes. I'll talk a little about more because that's probably where you're headed. R2 WinBugs interface to WinBugs. JAGS is specifically designed for R. There's Stan, it's faster. And then really, I haven't done a lot of Bayes modeling, did a little bit while I was up at Oregon State. But this is one where if you want to get into this, I would definitely dive in and find out what folks are doing within your discipline with Bayesian, or the closest discipline. If no one's using Bayes within your discipline and you want to bring something over from another one, that's fine. Just look at the closer discipline and see what they're doing. And that's